So picking up on where we were last time. So we are talking about chemical reactions. And we found that it was possible for certain kinds of reactions. Well, firstly, for every kind of reaction, it is possible to write, so we can write a differential equation using the principle of mass action kinetics. So that's pretty cool. Basically, what that means is that if I give you, for example, a synthesis reaction, with the rate, I can immediately use that to write the differential equation. So the change in the product is equal to this constant times the concentrations of each of the components. So we also saw that some systems are governed by linear systems of equations. And generally speaking, in order to have a linear system of equations, each reaction can have at most one component. And that is because if you look over here, this is the product of A and B. There's two components here. If your system of equations includes both A and B, then this product ends up being nonlinear. Over here, we will often state these kinds of equations in terms of single products. However, it's worth pointing out that if for example, B doesn't change. So for instance, if you're in an environment, this equation, if you're in an environment where there's so much B that reacting with A doesn't make any change to the concentration of B, then this is a constant, and the result is this ends up being linear. And sometimes this way of writing the equation is a shorthand for that. So there might, for example, be some kind of other product C, but if C's concentration doesn't change, we will often just not write it. In this kind of environment, we saw that with a forward and a backward reaction, we saw that the way to think about this was in terms of a differential equation, a vector differential equation, where I have this rate matrix R multiplied by that same vector. We talked a little bit about how to get the rate matrix. In this particular example, R looks like this. And we pointed out that the columns of R always have to sum to 0. Now, if I want, so starting with these observations, which are just a review from last time, I just want to make two additional observations. One is we're going to talk about the steady state solution. So if I have d by dt, I have this differential equation, d by dt of these concentrations equals r. Actually, let me make this a little more general. So I'm going to say let y be the vector of concentrations. Then, oh, well, for example, in the previous examples, we used y might look like that. It's the vector that contains the concentrations of both product A and product B in that reaction that is proceeding both forward and backward. And then we can write dy. Well, actually, let me write that down a little more formally. Then we can write dy by dt is r. There's my rate matrix. Well, r need not be 2 by 2 anymore. It can be the size of y as long as it's square. ry. So this generally is the master equation. And when we start talking about signal transduction, we're going to see a lot of examples of these and how to discretize them and to deal with them in discrete time as Markov chains. But for now, what I want to do is I want to think about the steady state solution. So at steady state, the change in concentrations is 0. So at steady state, everything is stationary. Everything is in its final form. If you think about the reaction, what this means is that it's in balance. Some A is being transformed into B at the same rate that the B is being transformed into A. Let me just write that to be clear. A is transformed into B at the same rate that B is transformed into A. What does this mean? So if I write down my master equation again, if this is 0 at steady state, then we must find y as the solution to ry equals 0. But if you know anything about linear algebra, then you will realize that the solution to ry equals 0 is the 0 eigenvector, i.e. the eigenvector at the 0 eigenvalue equal to 0. And that's easily seen. So we're basically looking for ry is equal to lambda y, but where lambda equals 0. So that's basically equal to the 0 vector. So that's a neat observation. The steady state solution is given by the zero eigenvector. This implies, by the way, that the rate matrix R is degenerate. That's always true because the constraint that all the columns sum to zero forces R to be degenerate. So there does exist a zero eigenvector, and you can always find it. So to find this, what we require, so to calculate, what we're going to do is we're going to calculate this for our simple example. So remember, R in our simple example was minus k plus, k minus, minus k minus. And what we require is that this, when multiplied by y, so this is R, this is y, that has to equal the zero vector. Okay, so the solution is pretty simple. You can find this a number of ways, but probably the simplest is to just do the following. We'll just multiply it directly. So minus k plus, k minus, minus k minus times AB is equal to negative k plus, excuse me, back up here. So top row times the column, we get negative k plus concentration of A plus k minus concentration of B. And then this times that, k plus concentration of A minus k minus concentration of B. And that has to equal 0, 0. So if I take the top part of the solution first, I have to have minus k plus A plus k minus B equals 0, which means k minus B is equal to k plus A, or A and concentrations of A and B are related as follows. If I know the concentration of A, then the concentration of B is k minus over k plus times B. And you can manipulate that in various ways. What you'll notice also is that if you do the same thing with this line, you'll get the same answer. That, I mean, you probably know that that's how eigenvalues work. They're not unique. So basically, this is the relationship between the concentration of A and B, and you can't reduce it any further. But that's good because it means that for any concentration A can take any value. There's a corresponding B that's in equilibrium with it. So there's no special values of concentration. It's just that if A and B satisfy this, then it's at steady state. So this then is the steady state solution. And the take-home message is that to get the steady state solution, find the zero eigenvector. And again, you don't have to solve it this way. You can crank up your favorite solver and type the eigenvalue find command and just figure out which one is the zero eigenvalue, and then away you go. but that's how you do it. And this is going to come up again when we talk about when we talk about signal transduction. We're going to be looking at these systems in discrete time as Markov chains, and this is this solution that we've just done here will come up again. I just want to talk about one more thing, which is we like to focus on linear systems because they're easy. That doesn't mean that if you have a nonlinear system that it's unsolvable. And the example that I want to give you is a very, very famous example called Michaelis-Menten. Kinetics. So Michaelis-Menten is a famous example of a nonlinear chemical reaction that can be solved. And not only that, but it is of these kinetics have tremendous importance to both biochemistry and molecular communication. And what it's all about is how enzymes work. So what an enzyme is, it's normally a protein. It's a particular kind of protein. And what it does is it catalyzes a reaction. So Michaelis-Menten kinetics basically talk about how they basically give you the mathematics of how these enzyme reactions work. And the idea is this: you start with a substrate. Sorry, let me redraw that a little nicer. Actually, I'm going to draw the substrate like this. And there's also going to be an enzyme. I got this backwards, excuse me. So this funny thing that I'm drawing like this is actually the enzyme. I'm going to give it the letter E. This S is going to be the substrate. What happens is that the enzyme and substrate will join up. So. And then the enzyme will act on the substrate to produce that's going to come away from the enzyme, but it's going to be something different. This is going to be called the product. Oops. So this is definitely something different. I'm drawing it a different shape. And I'm going to call that the product. So what we end up with is a series of chemical reactions that look like this. We start with the enzyme and the substrate. There's a forward reaction. There's a backward reaction. F is for forward, R is for reverse. So this is so far just a synthesis, and that is the part of the reaction where they get together. So that's from here to here. But then there's a further escape from the product where I get back my enzyme, but the now modified product. So this is the catalyzed reaction. I'm going to call that Kcat. So a catalyzed reaction, the catalyst always has to come out. So this is the catalyst that makes the reaction happen, but I always have to get the catalyst back. So knowing what we know about mass action kinetics, I can actually write down all the equations here. So E and S will have differential equations associated with them. Change in E. So some E is going to get plugged into ES, but the rate of that reaction is negative KF E times S. So over here, the things that react are E and S. So it ends up being E times S, KF, and a minus because E is being turned into ES. So I'm getting less E. Plus, coming back, the reverse reaction that creates E is this. That's K times the concentration of ES. And I also get E from the catalysis reaction from here to there. And that occurs at rate Kcat times ES. S is similar, ds. Sorry, that should be square brackets there. ds by dt. Okay, again, I get S starting here, coming back. Or excuse me, I lose S going this way, so that's the forward reaction. Negative KF ES. Oops. I gain S through the backwards reaction here. Sorry, this should be up here. This is KR. So KR ES, and I don't get S going this way. So that's the only way I can get S. So that's it. ES, I can lose ES through this reverse reaction and through the catalysis reaction. So that is minus KR ES minus Kcat ES, and I gain ES through this reaction. That is KF E times S. And finally, the product is what we're really interested in, and I only get that through this reaction, which is forward only. Sorry, this should be DES by DT, dP by DT is Kcat times ES. That's the only way I can get that is through this reaction. Okay, so what I'm really interested in, oops, sorry. This is what I'm really interested in. And what I'm further interested in is how to get that from the other products. So it turns out the way to solve this set of equations is to assume steady state. So we'll assume that this part of the reaction is in steady state. Now, we already established what that means when we solved the last set of equations. Now we can't go for the eigenvalues here because it's nonlinear. But what we can say is that the forward rate going this way has to be the same as the backward rate going this way. The forward rate is Kf ES, and the backward rate is Kr of the product E and S. What's more, we're going to call the concentration of E. So the only way, the amount of E initially is conserved. The amount of E initially, I'm going to call that concentration of E0, is conserved either in the present concentration of E or in the product ES. So in other words, all I can do with E is either turn it into a product or come back. So the current concentration of E is equal to the initial concentration of E minus the concentration of the product. So with those simplifications, I can start up here, or with this simplification, I can start up here, and I can say Kf times E0 minus ES times the concentration of S is equal to Kr times the product ES. So basically what I did is I took this guy and substituted him in here. So if I multiply through, I get Kf. Well, let's start with what we have on the previous page, just to be clear. And then what we can do is we can multiply through here. And then if we solve for ES, now just a second here, why are we doing this and where are we going? Let's just make sure we know. What we're interested in, remember, is the rate at which the product is produced. To do that, I need ES right here. I multiply by K cat. Come back here. Basically what I have to do here is I have to solve everything for ES, and that's pretty easy. I just take this guy over here and I divide through. If I do that, so basically I'm going to take this guy over here and divide, take out ES and then divide through. On the left, I'm left with Kf E0S, which is from here. And from these two terms, if I take that over here, I get KRES plus KFESS. I'm going to take out the ES and bring that back under. Oops. And what I end up with is KR plus KFS is equal to ES. I'm going to do one more thing here, which is I'm going to divide both top and bottom by KF And then I get E0S over KR over KF plus S is equal to ES. All right, so now I've done what I needed to do. I solved for ES. I can substitute that back into what I'm interested in, which is how fast is the product being produced. At steady state. So basically what I do, take that, plug it in here, and I get kcat E0S over KR over KF plus S. And finally, what I can do is what I'm going to do is I'm just going to pair this E with this K. And I get the following. Okay, I'm going to redraw that on the next page, make some remarks about it. So the rate at which the product is produced is given by kcat initial concentration of the enzyme times the concentration of the substrate divided by KR over KF plus S. Okay, I'm going to make a few remarks about this. So firstly, from here, this is the maximum rate, the maximum value of dP by dt. Oops. To see that, note that this value has to be positive. The minimum possible value you can take is 0, in which case this term becomes 1. And as this increases, this ratio goes down. So this part is the maximum possible value that this rate can take, and any other value of KR over KF other than 0 means that the rate will be less than that. The other thing to note here is that if you think back a couple pages, this is the steady state ratio. If you think back a few pages, we had these steady state relationships between A and B. Remember, A and B were a forward-backward pair, and A, if I had a certain concentration of A, the concentration of B was the reverse rate divided by the forward rate. So this ratio is actually important to those forward reverse kinds of reactions, just like this. This is the steady state ratio of forward to reverse. Excuse me, I should be a little more precise about that. Of products E and S to ES. This is also called, this has a special name, it's the dissociation rate. Or the dissociation constant. So I show you this for two reasons. One is because it's important in its own right, And to illustrate how to solve these kinds of equations, basically what we did, we transformed this equation is still nonlinear. It's nonlinear in S. If S is mostly constant, then that's cool. Then this actually does become quite linear, but it's still nonlinear. But we did actually manage to take this nonlinear family of equations right here, transform them into a single equation in P and S that has constants that are physically meaningful.